Lecture 17, Non-Renewable Energy, Take 1. Welcome to Unit 5, Earth's Carrying Capacity. This is the Introduction to Environmental Science for South Florida State College. This is lecture number 17. We're going to talk about non-renewable energy. A little bit of an outline for the rest of this unit. Lecture 18 is the Earth and its mineral resources. 19 is global air pollution. 20, water pollution, sustainability, managing a renewable resource. Look at these two graphics here. See if I've got my pen up. I think I do. Human population growth has certainly continued to increase. We've seen this graph before. We have this exponential change in our population. But most species, pick a species, this happens to be species number 5, reaches a carrying capacity. Right there, there's a limit. When are we going to reach ours? Well, that's a part of what we're talking about in this lecture, this series of lectures, this particular unit. So, starting off with Unit 5, Lecture 17. Now let me change, I did want that. There we go. Non-renewable energy. This is the outline for 17. We're going to talk about dependence on non-renewable energy, options with non-renewable energy, meeting future demands, fracking, oil shales, offshore drilling, and what alternatives do we have? Lecture 18. What are the Earth's mineral resources? What exactly do we mean by that? Extraction and exploitation, how we get those mineral resources wherever they're stored. Expanding those reserves and finding substitutes. Not always an easy thing to do. Unit 5 continued. Lecture 19 is going to be over global air pollution. What's the air made of? Carbon dioxide and other air emissions. Didn't used to be an emission, used to be just something that was naturally there, unless you're a volcano. Acidic deposition and how important it is. And ozone, stratospheric ozone depletion. And then water pollution. We're going to talk about sustainably managing a renewable resource. Surface water pollution, groundwater pollution, garbage patches, and dead zones. How dependent are we on this non-renewable energy stuff? How much do we rely on that? Well, that's a coal train. A lot of you may not have ever seen a coal train, certainly not one long as that. These things can run for miles and provide tremendous amounts of that coal, which is a very important resource. Coal trains are dominant features in parts of the United States. Are we diminishing our dependence on coal and these other fossil fuels? Well, supposedly. Though this goes back to 1635. This is before we were much of a country, but energy consumption in quadrillions of British thermal units. I'm not sure what exactly that means, but you can see how we've consistently been using coal since, well, about the mid-19th century. 1890 is where this, 1835, 1850. Coal has been one of those things we've used over and over again. There's this classification called other, and we started out using other first. Well, other is stuff like wood. That's one of the first fossil fuel that we used, although it's not a fossil fuel. There's other sorts of coal. Natural gas picked up and continues to actually be a source. Petroleum is an important source of fuels. Nuclear kind of has plateaued. It's that blue bar there. Among the other is solar and things such as that. So we have a tremendous dependence upon those fossil fuels. Again, back to that population growth, continue to increase. So has our energy use. Exponential. Same sort of a view as we've seen before. A lot of this is coal. This green area here happens to be hydropower, which is, well, a non-carbon, a non-fossil fuel use. Talk a little bit about that in a bit. A little chemistry, little bit of chemistry. Don't freak out on me, it's just a little chemistry. Let's talk about matter. What matter is? Matter has mass and takes up space. Coal, for example, a rock of coal. It's made up of elements that have certain unique properties, and those elements cannot be broken down chemically into other substances. Chemically is the key word there. Has to be, cannot be broken down chemically into other substances. And a compound is two or more different elements bonded together in fixed proportions. So more into this atomic theory, if you will, building blocks, what all matter is made of. So you have all matter is made up, elements are made up of atoms. And this particular atom, right here, kind of a nice model of an atom, cannot be broken down into simpler substances by chemical means. This one has, atoms have protons, neutrons, and electrons. And those are subatomic particles. Protons have a positive charge. Neutrons have no charge, that are inside this nucleus here, inside the nucleus. And then outside in this cloud that orbits the nucleus are these negatively charged electrons. In this example we have 6 protons plus 6 neutrons. This atom is carbon-12. It has 6 of those. This is carbon, the common name of carbon. You can change the isotope. You can have a different, isotopic form of an atom. Atoms with the same atomic number, 6 usually is the number for this, because it's the number of protons in the nucleus. The same number, same atomic number, but a different mass number. In the case of an element called carbon-13, it's a 3, you would have an extra neutron. It does not change the mass because neutrons have no charge, no mass. A little more on these building blocks. So, ions can either gain or lose electrons. You can have something that's positively charged. This is a sodium ion. It's an element. Or you can have a negatively charged something. This is a chlorine atom. Gain or lose electrons. They can form bonds between each other. pH, measure of acidity. So you can have hydrogen and then oxygen. Hydrogen is negatively charged. Oxygen is positively charged. Actually, it's 2 positive charges. And then the other hydrogen, also negatively charged. That's a measure of acidity, is the measure of how much relatively are there of these things, call them protons, in the water, versus what is in the OH, which is the negative part of it. The higher the amount of positive protons in the water, the lower the acidity of the water. We'll talk more about that. It's very important in terms of carbon dioxide, which forms when it dissolves in water, this stuff called carboxylic acid. It's causing a bit of acidification of the ocean. We can get a molecule, kind of drew up a molecule here. 2 or more atoms, the same or different elements, held together by chemical bonds. This happens to be water, which is H2O. We'll talk about that in a second. This atom, NaCl, sodium chloride, is salt, common salt. Very common, actually. The chemical formula In the case of water, there are 2 hydrogens and 1 oxygen, and that is characteristic of water. It's H2O, number of each type of atom or ion in a compound. Let's talk a little about the law. You didn't think you were going to study law today, but hey, it's environmental science. We do everything. Scientific law. One of them is a conservation of matter. When a physical or chemical change occurs, no atoms are created or destroyed. You can physically or chemically change them, but you still have the same number of atoms. You dissolve that, you take a block of salt and you dissolve it in water, and that block goes away, seems to go away, but it actually changes form, and the chloride and the sodium separate out. Those chemical changes happened, but no atoms were created or destroyed. To matter consumption, matter can be converted from one form to another, but there's really no away. When you throw something away, it's not really going to go away. You're going to convert it into something else, but it's still held somewhere in the environment, in our case. All right. Energy comes in many forms. We have this stuff called potential energy. This happens to be a lake, actually a reservoir, rather tall one. They're large. It's the headwaters of a particular river. And that water represents potential energy, stored energy. Can be converted, because it's being held up top here, into kinetic energy. Now, when you look at kinetic energy, you're really talking about what's going on here. That water were to be released and flow downstream, it becomes kinetic energy, something that's in motion. So water stirring past that turbine there is going to produce electricity. The same thing with heat. If you burn something, you take that wood has potential energy in it. When you light it on fire, it is going to be transformed into kinetic energy, and you can cook with it, or you can just let it burn, whatever you want to do. Transferred by radiation, conduction, or convection. And then we have electromagnetic radiation coming down from the sun as well. Energy changes are governed by 2 scientific laws. The first law of thermodynamics, known as the law of conservation of energy. It states, you see the quotes there? Yeah. When energy is converted from one form to another in a physical or chemical change, no energy is created or destroyed. Important points. Energy input always equals energy output, no matter how inefficient your vehicle happens to be. In my case, it's a 1996 Dodge Ram 1500. It's pretty inefficient, unless you're trying to haul a lot of stuff in the back. It's good for that. The second law of thermodynamics. Energy always goes from more useful to less useful form when it changes from one form to another. Think of gasoline, putting in the engine, that big old engine of my pickup truck. Gasoline itself is very, very useful. It can do has a lot of potential energy. Well, when I put it in the engine and it goes through gets exploded in the pistons, and all it releases energy, and the piston is driven down, and gas is released, air in other words, fumes, carbon dioxide, all those components that were a part of that, all the bonds that were held together inside that gasoline, they become the force that drives the piston, that turns the engine, that turns the wheels, but it also becomes all these fumes, carbon dioxide, water mostly. You can't get that back. You can't take the carbon dioxide and water and that heat and put it back together unless you're a plant, and it takes a long time. It's a different sort of a process. You get the idea. Energy is going from a more useful form to a less useful form when you do something with it, like put it in an engine and burn it. Energy efficiency or productivity. Now, that's a measure of how much useful work is accomplished by input of energy into a system. We also have a Prius. A Prius is much more energy efficient than a pickup truck. And it can do a certain amount, depends on what sort of work you're trying to do. Don't haul a ton of concrete blocks with your Prius. That won't work. Works fine in the pickup truck. Back to systems, we've seen this before. Systems have certain inputs, flows, and those outputs. When you look at a system, it's a set of components, like that engine, that function and interact with each other in some regular way. It takes inputs from the environment. In the case of the engine, it takes gasoline. Flows, throughputs, you put that gasoline through the engine, the fumes are exploded, you turn the piston, the gases are released, and then what comes out is those outputs back to the system in the form of heat, the form of the wheels turning, the form of carbon dioxide and water and other gases being released through the tailpipe. Outputs back to the environment. Again, systems respond to change through feedback loops. You can have a thing called a positive feedback loop, or that erosion experiment that was done in New Hampshire, where they cut they did clear cutting on the side of a mountain, and then they watched what happened, and it continued to erode. You continue to have more and more erosion off of that. It increased the gully size. Negative feedback loop causes the system to change in the opposite direction from which it is moving, like a house thermostat. So if it's warm outside and you have the air conditioner on, house warms up some, the air conditioner comes on, and it cools the house back down, and air conditioner turns off. Air conditioner turns off, that's the example of the negative feedback loop. So let's look at renewable, since we're talking about non-renewable resources primarily in this lecture. Resource, you've seen these before, I believe. Anything obtained from the environment to meet an organism's needs. Directly available for use, things that don't really need any processing. Things like you cut down a tree, you can pretty much burn it if you want to, or build something with it. But those that are not directly for a use, they have to be refined. And crude oil has to be refined. You have to pump it out of wherever it is, and then refine it in a process to get the usable parts. These things called perpetual resources. In terms of human time frames, solar energy is, we can't do anything about that. We can't change the amount of solar energy coming down. We can't divert it. We can't do anything except that it's going to be there, at least in human terms, in the human time frame. Renewable resources are things that will grow back or be refreshed, like forests, grasslands, fresh air, all that fertile soil. Sustainable yield. The highest rate at which a renewable resource can be used indefinitely without reducing the available supply. If you cut down the forest faster than the forest can grow back, you are exceeding the sustainable yield. So that highest rate at which a renewable resource can be used indefinitely without reducing its available supply is the sustainable yield. You don't always want to be at that point. Sometimes you want to be a little below that. So what do we do with non-renewable resources? Non-renewables, in human terms, exist in a fixed quantity or stock in the Earth's crust. So fossil fuels, one example. Metallic mineral resources, which we'll learn about in the next lecture, lecture 18. And non-metallic mineral resources, we'll also learn about that in the next lecture. As with perpetual resources, these are non-renewable in human time frames. Over millions of years, yes, the fossil fuels will be renewed. We will have organic matter that accumulates at the bottom of some ocean or something that is trapped there, and it will form more of this fossil fuel. But fossil because it's been buried for a long time. So how do we protect and preserve these non-renewable resources? Well, reduce, reuse, and recycle. Big proponent of that, especially with aluminum. It doesn't make any sense not to recycle aluminum, but I digress. It's a graphic put out several years ago, I think in the 70s, maybe it was the late 80s or 90s, I'm not sure, that projected where we were going to peak out in terms of the amount of fossil fuel use. And this is projected to peak, well, actually, about 2016, if you will. I believe that's the year they're kind of in the middle of that. World production the ultimate is 2,000 gigabarrels. That's how much oil is pumped out of the ground, and that's just a measurement. And 750 gigabytes non-conventional, which is all the way down here. It's non-conventional stuff. I think that's the 750 number right there, now that I'm looking at it. So, when it comes to conventional, we have crude oil, some oil shales, oil sands. The ways we get at those is what we're going to talk about next. You can see that over time, the projection is, and this is a long time, going out to 2075, 2100, you can see that it's projected that maybe that's the availability of fossil fuels. We'll have run out of them by that period of time, perhaps. So, go back to the carbon cycle. Carbon depends upon organisms. Plants are a fundamental part of the carbon cycle. The atmosphere is a consequence of this process of photosynthesis, taking that carbon dioxide into the plant and combining it with other molecules of carbon dioxide and producing sugars. And the process of respiration, which is what we do. We take those sugars, in a simple example, and we use them for energy to do what we do. Lecture in this case, or listen to a lecture in your case. And when we respire, when we actually consume those things, we give off carbon dioxide. We take in sugars and we give off carbon dioxide. In aquatic ecosystems, carbon dioxide has to first be dissolved in water before it can be used by the plants. Recall that although some carbon cycles very rapidly, like that carbon dioxide in the atmosphere that's taken in by plants, and then that carbon dioxide, the plants actually use that sugar for its own respiration, kicks that carbon dioxide right back out. Some stays unavailable for long periods of time. This is the carbon cycle right here. You recall that there is limestone, carbonate rock. It's the largest pool of carbon on the planet, and it's all locked up in rock. We can't take that and mine it and turn it into fossil fuels. At least nobody's figured out a way to do that yet. That might be next. Who knows? What we use now are these fossil fuel reserves that have been locked underground for millions of years. They're the past primary producers' work, fixed by primary producers, millions of years in the past. You see these rapidly rotating, if you will, but it's those amounts are actually unavailable for us to use in a practical sense, unless you're just going to burn trees. Trees do a pretty good job of taking in carbon dioxide, and we do a pretty good job of burning them sometimes. What we rely on, have relied on for 100 years or more, is this stuff called crude oil. Now, I remember seeing one of these in my grandparents' farm, not in Oklahoma or Texas, but in Louisiana. And we actually had this, it was smelly, because when they're pumping up all this stuff from the oil sands, you put out a lot of gas, sulfur dioxide and stuff like that. Fossil fuel was formed prehistorically, and it's stored down here in these oil sands, basically these sandy deposits where that oil still exists. And this pump essentially pumps that oil up and pops it out. Now, Ema and Papa never got rich off their oil well. It's just something to supplement their income as dairy farmers. It's pumped out of the ground and refined to produce a variety of products. What sort of things do you get from a barrel of oil? In this case, this barrel of oil is 42 gallons. Diesel is 12 of those gallons. If you have 42 gallons of crude oil, you get 42 gallons of diesel, 4 gallons of jet fuel. Some other products. Gasoline is the largest amount, but it's not a tremendously large amount. 19 gallons of that 42 gallon barrel of crude oil is gasoline. We ship it a lot of ways. Tanker over the ocean. We ship it by truck to our favorite gas station. Many places, and actually in most of the country, these refined products, whether it's usually it's liquefied petroleum gas, is shipped through a pipeline. We ship it by barge and by train. Seen a large increase in the amount of oil refined products shipped by train. But pipeline is probably I would say the safest, less environmentally impactful, except for, as long as the impact is large, unless you happen to be, your land happens to be in the pathway of a pipeline, in which case it is pretty impactful. Some interesting things that continue to go on. You may hear of short-term problems and with new pipelines. Well, those problems have been going on for generations. As long as they've been trying to put pipelines across land, people have objected to it. More on that in someone else's course. There's a variety of sources and extraction methods for this gallon of crude oil. One of them happens to be in the GOMEX, the Gulf of Mexico. Beginning in the 1940s is when we started to do this. First wells were in relatively shallow waters, these near shore areas, mostly off the coast of Texas and Louisiana, some off Mississippi and Alabama, none really off of Florida. Onshore sources in the U.S. Why do we go out the ocean? Why don't you just keep pumping it out of the ground? Because there's plenty of it there. Well, now we were starting to run out in the 40s. Increasingly hard to find. You go to the ocean because the easy stuff's been found, been already tapped, so to speak. So, near shore is easy. Well, guess what? We're going to tap that out too. Gulf is a very important source of crude oil for this country. We'll start I'm not sure what year that is. I believe it's 1980. Looking at that. And these are in thousands of barrels a day. So by 1985, we are relying on the Gulf of Mexico for 1 million barrels of oil a day. Dropped a little bit in the 90s. Then it's kind of been on an increase. You thought this was something that had been going on, it was old, it's not all that old. Looks like there's a peak in the early 2000s at about 1,700, 1.7 million barrels a day. We had these drop-offs. There was a recession in there. I'm not sure what went on there. Hurricane Katrina had an impact also. And then we jumped right back up to that point right there. It looked like the peak was about 1,800, 1.8 million, read the graph right, million barrels a day. A little bit of a slump after that, but you can see that the trend is the same. We still are relying tremendously on the Gulf of Mexico for crude oil. You may have heard of this. Let's see. Drilling rig, Deepwater Horizon. Deepwater Horizon is really designed to, just as the name says, go into deep water and drill for oil. It wasn't actually going to be a production well, it's how you create the well. You have to drill for it first, and then you cap that well off and put a pipe on it, and that pipe, that oil is under a lot of pressure underground. So, Deepwater Horizon, 5,000 feet of water. That's the shallow part. It then goes another 15,000 feet below the bottom of the Gulf. So that's 20,000 feet under the surface of the ocean is where they're going to get this oil. It's huge reserves underneath the ground. Why? Potentially one of the largest oil fields in the Gulf of Mexico. And we want to be able to tap into those things because our dependence on oil is not really slacking that much. The possibility was for this particular facility to produce 500,000 barrels a day. 500,000 barrels a day. Remember, the total amount that was being produced, or being produced now, is 1.8 million barrels a day. So it's a tremendous source if you can get to it. This is the actual picture of Deepwater Horizon. Floating platform, GPS technology, really cool things. There's a recent movie out about Deepwater Horizon. I have not seen it, so I cannot recommend or not recommend it. But if you're interested, I understand they did a really good job with the computer graphics to represent Deepwater Horizon. The oil industry wouldn't let them use an actual rig and blow it up, so they had to use CG. Oh well, what fun. It's a double pontoon format. Drilling portion is designed to detach, be lowered to the seafloor. It almost has an unlimited drilling depth. 5,000 feet. Well, I don't think they could go like in the deep bottom of the Pacific, but I could be wrong. Disaster happened April 20th, 2010. Remember, said that underground, deep underground, tremendous pressures. They're producing gas, as in methane, light gas. There's a tremendous explosion followed by a fire and killed 11 people. It broke the wellhead. Wellheads are not easy to break, a lot of pressure. And then there's this thing, we described it as a spill. I think Deepwater Horizon disaster is a more accurate way of describing it. But it's not really spilling like you would spill a glass of water, or, for example, if you remember the Exxon Valdez, or remember reading about the Exxon Valdez, which was an oil tanker that hit that ran ashore in Alaska. Gosh, in the 80s, I believe, is when Exxon Valdez happened. That was a spill where you crack the side of something and it spills out. Well, that's not what's happening here. This is what's happening here. This is tremendous pressure, that oil coming out of the ground. That's crude oil. This is a picture, and this is actually a picture of the wellhead 5,000 feet below the surface of the Gulf of Mexico. Deep Gulf is cold. Oil is lighter than water, but these are low temperatures, 35 degrees Fahrenheit, right down here at the bottom of the well. So the oil is going to come up a little ways, but really what happens, it becomes, kind of forms balls, it becomes viscous, it doesn't make it up to the surface because it's cold, it's congealing. Much of the oil, some of it went up, certainly the lighter stuff floated to the surface. Once it gets to the surface, if you put a little bit of gasoline in a pan of water, watch it float on top of it, and put it out in the sun, what happens? It evaporates. The same that happens with a lot of those, not a large volume, but the stuff you can see on the surface often will evaporate. But much of that stuff never made it to the surface. There's water pressure holding that heavier stuff down, and those gases and hydrocarbons were pretty much not dissolved, but sort of caught in the water. So this is those numbers from this Gulf spill, Deepwater Horizon. The Department of Energy, they're the low man on this totem pole, as sometimes they are. They estimated that in averaged release over the course of this spill, this event, which was from April 20th, 2010 to they officially shut it off. It was closed for all practical purposes about 3 months later, the 15th of July in 2010. DOE estimated there were 60,000 barrels per day released. Total number of barrels released, 3 million barrels. So when you talk about barrels, a barrel is 42 gallons. So multiply that by 42 and you have 120 million gallons. BP, in their worst case, said no, it's more like 100,000 barrels a day. Same with, I think the Associated Press came up with the same number, but it wasn't their worst case, it was an actual, probably real number. The official tally, I think, came out to 200 million gallons. 200 million gallons of oil released. That's the largest amount of oil ever released from an oil spill, if you will. There have been ones that went on for longer, but nothing has put out that much oil. Let's look at what happened with that oil. Remember, it's not going to the surface. It's not just popping up, or some of it's not popping up. Some of it mixes with those oil particles and sinks. This marine snow ends up going down to the bottom of the ocean. At the surface, they're applying all kinds of dispersants because you don't want this stuff to get on the beaches where it causes all kinds of havoc, and rightly so. You don't want it there. So you put these things called dispersants on it. Those dispersants either try to break it down or they coagulate it to make it heavy, and it sinks. Okay, so it's not going on under the estuary here. That's a positive thing. You don't want to put it there. Since we're off the mouth of the Mississippi, some of it is mixing with river sediments. Lots of mud, muddy Mississippi, and that's sinking. The fourth pathway, they had this stuff called deep kill that they injected actually into the plume. That stuff kept it out of the surface, and it sank. See a theme here? Some of those byproducts of the surface, they actually lit fires on the oil to keep it from hitting the shore. We like this. Except those burned oil byproducts, the tars and stuff, sink. And then those tar balls that actually make it to shore, they mix with the sand, and they also sink. So you have a lot of oil reaching the bottom of the Gulf of Mexico. Don't know if they're still burping up, if you pardon the term, oil tar balls from the bottom of the Gulf, although I think they will be for generations. And some of it came from Deepwater Horizon, some of it didn't. But a lot of the oil right now floating around the bottom of the Gulf of Mexico, well, it's staying there, is from Deepwater Horizon. So there's where the rig was located, 5,000 feet deep. That's where the wellhead was. That plume moved, and still moving, several years later. It has probably reached this thing called the loop current of the Gulf Stream. And you can probably find it in the Gulf Stream, on the bottom of the ocean. I don't know how far around the globe it has made it, but it's still there. What are the impacts? So we have these various ecosystems, near shore in particular. We have these wetlands. Wetlands are beautiful things, saltwater marshes, some estuaries, it's very, very abundantly rich, a tremendously productive environment for spawning areas for fish, refuge for birds, nursery areas for crabs, all those sorts of things. You have the nearshore, the stuff called nearshore benthos, oysters and things like that, shrimp. Filter feeders, they have to filter their water, that's how they get their food. That's their MO, if you will. You have these algae growing in the photic zone. The sunlight can penetrate to 200, 300 feet, and you have things growing throughout that. And then you have the top predators, these tuna, marine mammals too, and some birds, but those are the top predators. And then you have, actually deep in the Gulf of Mexico, you have deep water corals. You have coral growing down deep. Very diverse system in the natural Gulf of Mexico. So, impacts. In those wetlands, we're trying to keep that oil out of the wetlands. But if it reaches the wetlands, you're going to have degradation. It's going to erode the marsh. Probably going to reduce, because oil doesn't lend itself to good forage fish. It doesn't lead itself to good habitat. Nearshore benthos, remember those are filter feeders, oysters and shrimp. It's going to prevent them from actually filter feeding. In the photic zone, putting all those dispersants out knocks a lot of the algae that were growing. So you have this breakdown of the food chain. Those top predators are going to start having a hard time finding the lower level predators to eat. And then the deep benthos, those tar balls are just going to roll over, and are rolling over, a lot of the deep coral. More on this, the University of South Florida continues to contribute to this work, this study, and there is an article that will be on the course homepage that you can hopefully still link to. It's a newspaper article, and newspapers change. I certainly hope it's still there. If not, I'll find another one at any rate. Work will be going on for a very long time in the Gulf of Mexico to see the impacts, study the impacts of Deepwater Horizon. A little different spot, Alberta, a little colder. The things called oil sands, and this pipeline that carries oil, does carry oil, from these Alberta oil sands in Canada. Stuff is bitumen. It is solid below 50 degrees Fahrenheit. It's like molasses. And it's mixed in clay and sand. So to get it out, you got to inject steam into it. So you got all this steam injection going on. I gather that you get more energy out of injecting steam into this bitumen than you do from actually producing the steam. The extract is then upgraded, mixed with other fluids, so it can be piped. These are the largest oil deposits in the world right here in Alberta. And Canada wants to be able to take advantage of that. The Keystone Pipeline. It's in existence, it works, it's happening right now. It has been for many years pumping liquefied oil sand through this existing pipeline. So we have this Keystone Pipeline that actually flows from there down to Cushing, Oklahoma. I mentioned Cushing because we'll talk about earthquakes in a minute, and Cushing happens to be the epicenter of a lot of earthquake activity for a different reason, not related to the Keystone Pipeline. Some of that oil actually goes over to Illinois right now. If you can see the dotted line on this map, I kind of paralleled it with that red line there. That's where there was a proposed expansion called the XL, so we could get that oil. Don't stop in Oklahoma, don't send it to Illinois, take it straight to Texas, because that's where the big refineries are. They can refine more oil. The permit was denied by the federal government for a variety of reasons. Some of it was economic, mostly, environmental would have been a good positive reason for denying it, because do we really need to be putting more pipelines across the country? Really, it's probably politics. But the alternative to a pipeline is a tank truck or a train car, which is probably less environmentally safe. Let's look at another way of getting oil out of the ground. Here we've gotten Deepwater Horizon, we've got Keystone XL, now we're talking about fracking. We've seen fracking before in 5 easy steps. So, step 1, take large volumes of water and deliver them to the site. Because you have to have a lot of water to frack oil, to hydraulically break up that oil. Second step is to chemically add this stuff called propant to that water. It's kind of a granular substance, probably has some clay and stuff like that. Once that water is injected into the ground, the propant is used to keep it opens those cracks underground, these fractures down here, to make that hydraulic fracturing fluid. Step 3, stuff wouldn't work unless it was under pressure. So they inject this fracking fluid into the well, and it cracks. It's a lateral well. Creates cracks in geologic formation, and the fossil fuels escape the well and are collected at the surface in various ways. So you keep that pressure on, then you release the pressure. What's going to happen to all that fluid? It's going to come back, called flow back. Fluid has been injected in the well, as well as the fossil fuels. That's the goal. The goal is not just to inject water in the ground under pressure and crack the ground. The purpose is to actually release that oil. Flowback has to be stored because it has propane in it, it has petroleum hydrocarbons in it, it has all kinds of things in it. You can't just let it flow on the ground. You have to collect that stuff because it is hazardous. And 5, what do you do with that leftover wastewater? Well, often it can be re-injected back underground. Oops, there we go, re-injected back underground. It can be disposed of in surface waters. Ooh, I don't like that one. Can be recycled. That would be good. Recycling. Basically, you have to clean it up some, but use it for future fracking operations. That's probably expensive. And fracking is a very important source of fossil fuel and a source of our independence for the U.S. You'll know more about fracking and how to go about it. That is the link in the EPA. So, fracking, is there any impact really? Well, we have these advanced extraction techniques. Fracking, just described that. This is an actual, the previous was a conceptual diagram. This is more actually what's happening in there. Conventional wells are located, this is a diagram from Oklahoma. You can just drill conventional wells that don't get into anything. They do not do any good. They get dry wells, whatever it is. And then you have this fracking well that goes down, releases that shale oil, and it all comes up and it's collected by a conventional well closer to the surface. It kind of gets trapped in that seal layer, and that conventional oil well is able to actually collect a lot more gas and oil than it was previously. Fracking is practiced all over the country. Well, not the blue areas. Not a lot of oil in those blue areas. Particularly in Texas. Texas has the largest number of fracking wells. Remember that Texas was the center of the oil boom. Pennsylvania has an awful lot of fracking wells too. Texas, 14,000. Pennsylvania, only 2,000. The price of oil is pretty low right now. I'm not sure what it's selling for per barrel. When fracking was at its height, a barrel of oil was selling for 3 or 4 times what it sells for today. I'm recording this lecture at a certain period of time, remember that. But it was much more economically viable at higher prices. The price of oil has been pretty low, but we still keep fracking. See those areas where fracking is most common right there in the central part of the country. This is one of those impacts. Remember I talked about Cushing, Oklahoma. Cushing is about right there. Mentioned Cushing because recently to this recording there was a magnitude 5 earthquake in Cushing, and that's a big deal, particularly with all those oil distribution centers in Cushing. But Oklahoma earthquakes, this goes back to 1979. Really, they recorded this. These are earthquakes greater than 3 magnitude being that seismic magnitude. And really there's no change. This is, which went back to 1979 for that period until 2007. Then all of a sudden, and it is all of a sudden, there's this ramping up tremendous increase. In 2015 there were 587 earthquakes greater than magnitude 3. That was a lot of earthquakes. You can see this is a picture, a fairly short timestamp of when there were earthquakes happening. And those are all areas where fracking has occurred, but it's not the fracking that does it. It's not really what's going on. There's an assignment on this. It should be available as soon as you have viewed this lecture. Annual Oklahoma earthquakes, magnitude 3 versus average oil and gas drilling rig count. Number of earthquakes are these blue bars. Number of earthquakes greater than magnitude 3, because honestly, apparently anything less than magnitude 3 happens all the time, all over the world. Can't feel them. 109 in 2013, you can see that that's about the same period of time when the horizontal rigs increased. But I'm not going to give away what the answer is, because you saw a drop here in the number of horizontal wells out there, but you saw an increase. This is the total number of earthquakes in 2015. That's a different number I had before, but it's still a lot. 941 earthquakes in 2015. So, see the assignment. It's a good one. What choices do we have, though? Can we get? We're locked into having lights that are burning based upon the fact that we're burning coal or we're burning other sorts of fossil fuels. Well, certainly there's solar. A lot of talk about solar, a lot of need for increasing in solar, my opinion, but we're going to run out of fossil fuels. Wind. The wind is a continuous source. It always has been. How do we tap into that without damaging the environment? The huge wind farms in parts of the Midwest that are generating a lot of electricity, but they're also having tremendous impacts on bird populations, because birds don't know how to fly around these things. I don't know how that works, but anyway. The ocean waves, why can't we tap that? I mean, that's always going on. And then there's this idea of geothermal, like the geysers out at Yellowstone. Old Faithful make a great geothermal source because it's consistent. Geothermal, that underground heat and water, in a lot of places in the world where it's acceptable. I believe the nation of Iceland, tremendous amount of volcanic activity, tremendous amount of geothermal. They have been able to tap into that and generate most of their electricity just from that heat underground. So they're very carbon neutral, or carbon negative, if you will. They don't use very much at all. So these are no carbon. Hydroelectric, talked about this dam here with the water flowing over the sluice gate, taking that potential energy of the water and turning it into kinetic energy to turn the turbines. All of these things do the same thing. Then there's nuclear power. Nuclear power, there's very, very few new nuclear power plants are being built. I think in the last 15 years I'm aware of one or two that have actually come online, that have become active. Far more have been closed down, largely because of the waste, but that's a different issue. Nuclear energy. How renewable is nuclear energy? So, this is kind of a closing slide, a sunset slide, if you will. Nuclear energy uses the process of fission. Fission is also what powers those nuclear boats in the Navy. Fission is a different process where you slam two atoms together like the power of the sun. Well, we would have a great way of actually controlling that. We haven't figured that out yet. That would be an completely inexhaustible source of energy, because you can always slam two atoms together. We got a lot of those things. Fission is what we use today. Is fusion the future? Perhaps it is. Talked about our dependence on non-renewable energy, how it has increased. Got this nice graphic here. Boom, looks like human populations does the same thing. So what is energy actually? Talked about the laws of thermodynamics, potential, that water at the top of the reservoir, versus kinetic energy. The meaning of what's non-renewable mean? What is non-renewable in human time frames? Talked about how we're meeting the future demands, from Deepwater Horizon to those oil shales, tar sands, Keystone XL, and hydraulic fracturing. And those other options, solar, wind, the ocean, waves, geothermal, hydroelectric, and nuclear. So references from this lecture. Some really good references down here on Oklahoma earthquakes. I might just make that a discussion forum. I think that'd be great.